Hi, my name is Haishan Gao. In this video, I will present my final project for Stanford CS 330. Large language models are observed to have a particularly interesting behavior that we call in-context learning. Models with in-context learning ability can perform a new task conditioned on the prompt without seeing the task during the training time. Such ability is surprising because the distribution of the pre-training documents is usually not matching with the distribution of the prompts. Prior research studies have shown that the large model size and certain data distribution, such as burstiness, are essential for the occurrence of in-context learning. In this project, we investigate how some other data properties, such as diversity, affect the model's in-context learning ability and its ability to generalize to unseen concepts. To study the problem within a course scope, we use a small-scale synthetic dataset designed for studying in-context learning. We propose a definition for data diversity in this work, and the result shows using diverse data can lead to better generalization to unseen concepts, whereas increasing the model size does not help with out-of-distribution generalization. The synthetic dataset we used is called JINC, proposed by Xie et al. JINC dataset is generated with latent concepts formulated by transition probability matrices of hidden Markov models. For example, we can consider Wikibio as a latent concept, since the text usually follows the sequence of the person's name, nationality, occupations, etc. When using such text for pre-training, the prompt could have very different distributions. In the example showing here, the prompt consists of short sentences and delimiters, which is not seen in the training data. The paper proposes when the difference between the true concept and any other concepts is greater than the error from the low probability transitions, in-context learning happens. It also shows that model fails to extrapolate to novel concepts. Our work is interested in exploring what could enable the ability to extrapolate, and our hypothesis is that by training with more diverse data, the model could have better ability to extrapolate. To test that, we propose a definition for the training data diversity as the average pairwise similarity of hidden Markov models from which the concepts are constructed. We use KL divergence of two hidden Markov models as the pairwise similarity. We use a computational simulating method to estimate the exact KL divergence. We then generate synthetic datasets with the following settings. We use different concept numbers from 1 to 9 and different data diversity from 0.15 to 0.8. Next, I will talk about the experiment settings and the result. The training task is to predict next word using the generated datasets. There are two types of prompts used during the testing time. One is generated with concepts already seen during the training time, and we call them in-distribution prompts. The other is generated with unseen novel concepts, which we call out-of-distribution prompts. We have 2,500 prompts for each. We then train models with different architectures and settings. The result shows that by using more diverse data for training, the out-of-distribution accuracy has increased from 5% to 25%. We also discovered that increasing the model size does not help with out-of-distribution generalization. Another interesting finding is that even when pre-trained with datasets that have very low data diversity, the model can still exhibit in-context learning ability. There are several takeaways from this project. First, using more diverse data for training is more important than using more data for training. Second, scaling model sizes may not always help. Next step to this project could be testing out the hypothesis on some real-world data. Here concludes the presentation. Thank you so much for listening.